Hello everyone and welcome to another video of the series Quantum Hidden Champions here on the Polaris School of Quantum. In today's video we are going to look at TOPTICA, and with that I would say let's hop right into the website and figure out what they are actually doing in the area of quantum technology. So here we are on their website. It says TOPTICA up here. You see some laser here, which is pointing at some crystal and making cool light effects. There's also a funky research mouse here, and a cat, and some more laser. Oh, sorry. Oh. We go back. Some laser up here. Then so as per usual, let's scroll down the page. So here it says diode lasers, ultra fast fiber lasers, terahertz systems, frequency comms, and laser rack systems. Quick note ahead, I'm not an expert when it comes to, let's say, optical components. So I will not go into the details of all of this, right? It just says high-end laser systems for your scientific or industrial application. And then here we see the applications, and one of them is of course very prominent for this specific series, which is measurement and processing. No, I'm kidding. It's quantum technologies and spectroscopy, of course. So that's what we are going to look at. But before we do that, let's scroll down a little bit further. So here it says latest news. There are some different news here if you go through it. So it says launches TerraScan Ultra, then there's some vice president appointed information here, and becomes a European company as well. The legal change became effective, register of Munich local court under this number, so Munich-based company in that case, I guess. All wavelength, so it says from 190 nanometers to 0.1 terahertz. TOPTICA Photonics has been developing and manufacturing high-end laser systems for more than 25 years. The systems are used for demanding scientific and industrial applications in biophotonics, industrial metrology, and quantum technology. TOPTICA is renowned for providing the widest wavelength coverage of lasers on the market, providing high power lasers even at exotic wavelengths like 190 nanometers all the way up to 0.1 terahertz, corresponding to 3 millimeter wavelength. Quick note on the wavelength. So the color of your light that you're seeing, or the color, let's start with that. So light is electromagnetic radiation. So basically photons, they are electromagnetic oscillations, more or less. Quantum particles, right? Or quantum, let's say quantum particles. Of course, they behave also like waves, right? You have this wave-particle dualism in quantum physics, where quantum particles can also behave like waves. And now, how do they differentiate? So what is the difference between them? What is the difference between a green photon and, let's say, or not a green photon, a blue photon and a red one? It's actually the wavelength that you are looking at. So they have so if you think about the electromagnetic wave traveling through the space, there's some length at which it oscillates, because it always moves with the speed of light, right? This is Einstein theory of relativity. Photons always move at the speed of light. And now the wiggling at which this electromagnetic wave is penetrating, so at which frequency or at which length actually this oscillation is happening, that is the wavelength. And usually when you're looking at the optic spectrum, you are in the nanometer wavelength. That means that's the reason why, for example, ASML has to go to this very ASML, the company was also featured earlier in this series, which is making the UV light machines. They have to go all the way down to ultraviolet and extreme ultraviolet, because if you want to resolve these very, very small, tiny transistors in the single-digit nanometer scale pitch, then you need to go all the way to this very extreme ultraviolet side of the spectrum. Then if you go up, so you come into the violet range, then the blue range, all the way up through the color scheme, all the way up to the red, and then infrared range, which is already again what we cannot see. So ultraviolet and infrared, ultraviolet and infrared are basically the borders of the range that is visible in the electromagnetic spectrum to our eye. And then if you go up from there, you come into the terahertz regime. So that's like, again, then electromagnetic waves, but outside of our spectrum on the long side. And then, of course, if you go further, you come into, let's say, the microwave regime, so radio frequencies, gigahertz regime, things like that. And this is noted here. So 0.1 terahertz. So hertz is a frequency now, and nanometers is a length. That's why they translated it here using the speed of light. You come to this 3 millimeters of wavelength. So actually something that is already pretty microscopic. It's millimeters, right? So that's quite a broad range of optical instruments, and TOPTICA is catering to all of them. And I mean, I'm choosing that because, of course, when I was working in different labs, there were also people working with quantum technology and optical. So like quantum dots, for example, optically active quantum dots, because there is this idea of, let's say, you could have a quantum information encoded in some electrical signal or in some particle like an electron spin, and you could then convert that into an optical signal that you can then transfer via a fiber, for example, over a long distance, which is otherwise much more difficult when it comes to these quantum systems. So moving quantum information requires, if you want to go long distance, usually to transform the quantum information into optical property like a photon. And that's where, you start to look into this whole optics related topics. But then also when you think about systems like ion traps, for example, in ion trapped qubits, you also might rely on actually exciting ions into different states. And that usually also happens with optical components. You might want to do things like, Doppler cooling and other laser cooling related technologies. And for that, you need specific lasers. And that's where this whole world here starts. And we will check that out in a second. But before, let's quickly go also into the products and the applications. So actually, I think it's very nice to see that this is very structured here. So you have, even in the products, you see the different areas that they're catering to. So like biophotonics and microscopy, measurements and processing, and then quantum technologies and spectroscopy. And you can actually see that the last one is pretty much, let's say, the biggest one in the offering right now. So again, also in this case, TOPTICA is one of the companies that are enabling the quantum field to actually evolve. They are building, let's say, the basic building blocks that are needed to actually build those fancy quantum applications on top, which in this case are listed here. So you have the tunable diode lasers, you have laser rack systems, frequency comps, there's optical isolators and photonical optical isolators, wave meters, and laser analysis meters, and then there's fiber lasers and amplifiers. Then on the application side of things, again, we see the biophotonics, the measurement processing, and the quantum technologies and spectroscopy here now listed by the different applications. And there, again, as I mentioned before, you see, for example, here, ion laser cooling and trapping. So this is referring to the ion traps, where on the one hand, you need maybe the laser to engage with the ions, but also for the cooling, because again, like in the other systems, you might not need a cryostat here to cool the ions, but still, in order to reveal their and control their quantum properties, you need to actually cool them down, and there are different ways to do so. And one of them is also the laser-based cooling. And if you're interested in learning more about that, please let me know down in the comments below. I'm happy to create a video also on this specific topic. Degenerate quantum gates, there's all optical pumping, Rydberg excitations, and then what I also mentioned before, quantum dots and microcavities. There's also the other quantum technologies. So we see here quantum communication, and then also sensing and metrology, as well as spectroscopy. So it's catering to the whole stack. So from quantum sensing over to communication, quantum communication, all the way up to things like here ion traps, which are then used for quantum computation. There's also other stuff here like microwave generation. I talked about microwaves also before. And then there's the astronomy and geology side of things, which I'm not sure if I would count that as the quantum technologies, which also I think they don't, but it looks like, because there's like this column here, but it includes like laser guide star, LiDAR seeding, and distance metrology. There's also something about all the different technologies they are using. So there are technology tutorials explaining how these different technologies work. And I'm not going to go into detail here because I'm not an expert on all of these different ones. I just know that the frequency comms are very, well, not super recent, but actually within the last years, they have been a Nobel Prize topic. So the researchers that discovered or built these the first time, actually in Germany, partially, I think, maybe not even only partially, but in Munich, there's actually a research center where I think major parts of this frequency comms development has happened. Then there's some other stuff here. So it says TOPTICA proprietary, I guess, technologies, and they are all listed over here. And then there's also some Python Laser SDK, which software development kit SDK relates to the software that you are using to control these. It's very nice to see that they have a Python one here as well, because I think Python is one of the most spreaded programming languages when it comes to scientific lab automation frameworks and so on. There's also some information about the company, which we will dive into in a little later. But for now, let's take a look at the quantum technologies here. So I will click on this. I hope I didn't destroy anything here. There we are. So here we are now in the product category of the quantum technologies. And what does it say? So compact, robust, high-end environment. I'm not sure if I went to the right one, because here it doesn't say. It goes into frequency comms and not into the quantum technologies. Let me go back. Maybe I did something wrong here. And then open it again. Okay. So you have to choose one of those. No, then we do it differently. We go here into the applications and then into the quantum technologies. Let's, as an example, check out, for example, the ion laser cooling and trapping. So this is the site. What is actually quite nice, I think, is this visualization here, even though quite low resolved, of a ion trap. So this is usually how this ion traps are being built. So you see this is a linear ion trap. So the ions are sitting one to the next one, like on a pearl chain. They are sitting all on this one-dimensional area here. This is done with electromagnetic fields that are dynamically changed. And then I guess what it says here, TOPTICA lasers are widely used for ion trapping experiments. The picture shows the schematics of an ion trap at PTB Braunschweig in Germany, and CCD camera picture of fluorescing trapped ions. And then there's also some explanation here. So it says ion laser cooling and trapping with diode lasers, customized solutions for ion laser cooling and trapping, ion traps, ionization of neutral atoms, laser cooling of trapped ions, and coherent manipulation of ions. So these, I guess, are the things that the lasers are being used for. So ionization of neutral atoms, because usually when you find atoms in the environment, like if you, for example, isolate helium, just as an example, you will usually not find helium ions, so with one electron missing, for example, but usually they are, because that's the most stable state, they're sitting there as isolated single helium atoms. And for example, if you look at hydrogen, usually you have two atoms that are sitting together, that are bonded together, H2, right? So then you need to first split them apart, and then you also need to make these neutral atoms into ions. And this is something that lasers can also be used for. There's the laser cooling for the trapped ions. I mentioned that before, as in using lasers to actually remove, for example, atoms that are too hot, that have too much thermal energy, but then also using techniques like Doppler cooling to actually cool down atoms or ions actually. And then finally, there's this note here on the coherent manipulation of ions. This is when you, for example, want to build a quantum gate. Then it says here you can learn about the different types of traps making ions out of atoms. So this is this ionization stage. Different ways of ion laser cooling. So actually, I think this is quite nice because you can see a lot of information about these various different stages, and can also learn a lot about where the lasers are being used and what they're actually doing. So there's various types of manipulation, and then TOPTICA's added value. Ion trapping and I will go through that one here now. Ion trapping itself relies on static or RF electric and static magnetic fields. So no lasers are needed here. However, selective ionization and cooling require tunable lasers at the right wavelengths, which are usually in the blue or UV spectral range. Those wavelengths are most conveniently realized by frequency converting high power CW diode lasers. Depending on the ion, frequency doubled or even frequency quadrupled diode, laser systems are needed, usually in conjunction with other lasers for optical pumping or coherent manipulation. TOPTICA offers customized solutions for one requested wavelength. Usually also complete packages are available for selected ions. If lasers with extremely small line width, for example hertz, are required, TOPTICA is the right partner for your attempt to actively narrow the line width of a special version of an ECDL diode laser. Our locking modules for fast feedback are unique, much faster than any other solution on the market. We also supply a versatile function generator of VFG, which allows one to phase currently address lasers, for example, using acousto-optic modulators, AOM, for coherent manipulation. Discuss with TOPTICA experts that have strong interest and expertise in ion trapping details of your experiment. And maybe that's also important to mention. So it's also mentioned here. They are catering to this very, let's say, scientific applications, right? And for that, you also usually need to have experts. And it's nice to see here that it even calls you to discuss with the experts. So they, I think, have a very strong understanding also of the applications. I mean, you see, they create all of this content as a starting point just for you to understand, let's say, the basic applications. And then you can also contact, it's a call to action on this page literally, to contact an expert. So they really show here that they have a deep expertise in this specific application, and that they exactly know which products you need to have to quickly get from, let's say, an idea, a proof of concept, all the way towards an actually working, for example, in this case, ion trap. There's also related applications here. You see there's an article and also a brochure with relevant information. And I assume that it's going to be like this for most of the topics here. So you can also see here degenerate quantum gases. So BEC, Bose-Einstein condensate. You see that here, degenerate Fermi gas, tuning interactions in degenerate gases, BEC of molecules, and degenerate gases and optical lattices simulating solid state physics. And that's again, let's say, I think some companies call that, let's say, analog quantum computing or whatever. It's using basically cold gases, degenerate gases, putting them with lasers into optical lattices and thereby simulating different properties of quantum systems by modulating different factors like, I don't know, the position of the atoms or the way that they are ordered, and thereby emulating more or less, for example, a crystal. And again, you see all of this information here. There's also other stuff available, so there are also other topics here. There's applied quantum technology. You can also quickly check that one out. Here it goes into sensing and metrology, computing and simulation, communication, spectroscopy, frequency calm spectroscopy, and so on. There's also a note here on European flagship projects and German quantum technology projects, like, for example, here, the Quantentechnologien one from Germany and the quantum flagship from the European Union, where they are, I guess, supporting with the expertise and then also helping research labs that are involved in these to build their lab setups. Let's quickly hop into sensing and metrology just to see what are the applications they're catering to. As per usual, it's very nicely structured here, so we can quickly check this one out. So time and frequency, fundamental constants, and tests of fundamental theories. So this is like, again, I think close to what we saw with the PTB Braunschweig before. So this is like metrology as in standard definitions, like think about atom clocks and so on. Then it says that's in the fundamental constants, Then there's atom interferometry, rotation and acceleration, laser-based trace gas analysis, nonlinear magneto-optical rotation of B-field measurement, magnetocardiography. So that's like here it says also measuring the heart's magnetic field. So that's like a very medical or biomedical application. And the same is also being done here for the brain, so brain magnetic fields. And again, you find all the explanations down here as well as additional material on that. Then there's also the quantum communication, and that we will also very briefly check out here. So using lasers for quantum information, quantum computing, quantum teleportation, quantum cryptography, and sources for single or entangled photons. There's some basis on the quantum technologies, high speed with quantum computing, state transfer with teleportation, secure communication with quantum cryptography. And let's quickly check out this one. Quantum cryptography uses quantum physics properties like entanglement and back action of the measurement process on a quantum state to achieve secure communication between a sender, Alice, and a receiver, Bob. The standard approach is that Alice and Bob perform measurements on entangled quantum systems, usually entangled photons, in order to create a key for Alice and Bob. Since they can use this code to encrypt and decrypt the real message, the quantum cryptography method is called quantum key distribution, or QKD, which we've also seen previously in this series here, that there are some companies active in this area. The real message is encrypted by Alice according to her measurement results and sent through an open channel, so anyone is allowed to listen, to Bob, who decrypts the message according to this measurement. Any eavesdropping, so any attempt of a third party to detect the quantum key, can be detected because according to quantum physics laws, each measurement influences the quantum mechanical state itself. Eavesdropping would be noticed always. So you can do that by some correlation measurements, and then you can actually figure out that somebody's eavesdropping into the system. And this is a secure way because the key that you're using, which can be a random key, right, the key is as long as the message itself. So if you have, for example, a message that, I don't know, is 1000 letters long, and you use a very simple key, like you, for example, just add to every single letter 2 characters. So instead of A, you go B, C, and so on. It's actually quite simple to use different methods to figure out what is your key and then to break the encryption. But if your key is exactly the same length as the message, and it's a completely random key, for example, there's no way that you can use correlation measurements or anything to kind of crack the key. And also here you can, the key is generated, and at the same time you can not, let's say, sniff into it and listen and figure out what the key is, because this can be detected. Okay, back to the text. So due to this obvious significance, quantum cryptography research is pushed a lot, and many results have been achieved so far. Quantum key distribution over hundreds of kilometers in fiber or over whole cities in free space was shown already, while satellite links of entangled photons between Earth stations are currently explored. To prove the usability, a quantum encrypted bank transaction was undertaken. So that's a very nice and concise explanation here. And again, there were also companies already in this space that we've briefly touched on in previous episodes. So go check them out if quantum cryptography is interesting to you. Now, finally, let's quickly check out also the company profile side. So here it says key facts: founded in 1998, around 600 employees over the whole group, and a revenue of 140 million euro or 155 million US dollars over the whole group. There's this European Society legal form. You see the executive board and the chairman over here. So TOPTICA Photonics SE. TOPTICA develops and manufactures high-end laser systems for scientific and industrial applications. The portfolio includes diode lasers, ultrafast fiber lasers, terahertz systems, frequency comms, and continuous wave fiber lasers and amplifiers. OEM customers, scientists, and over a dozen Nobel laureates all acknowledge the world-class exceptional specifications of TOPTICA's lasers, as well as their reliability and longevity. Founded in 1998 near Munich, Germany, TOPTICA became one of the leading laser photonics companies by aiming for and consistently delivering high-end specifications. TOPTICA's diode lasers are appreciated for excellent coherence, wide tuning range, and ideal beam profiles. TOPTICA's 600 employees worldwide take pride in developing customized systems in close collaboration with several universities and institutes. Latest scientific discoveries are frequently incorporated into commercial products. With a global distribution network, TOPTICA provides exceptional service worldwide. And then there's some more information here. So TOPTICA Photonics officially belongs to Bayern's best 50 companies in Germany, in Bavaria. There are some key markets mentioned here. That's what we saw before, and some key technologies that we've seen in the text previously. Let's quickly also check out here on the people part. So we see the executive board, and also the management. So that's, I think, very transparent to see all of the people that are actually working there. There's also something on the worldwide presence. Here you see all the different locations. So this is, I guess, Bavaria in Germany. But you can also see there's in the US, there's also in Asian Pacific area, a lot of different distributors and also offices of TOPTICA themselves. Okay, and here we see the whole list of places. I think with that, let's call it today's video. As usual, make sure that you subscribe to the channel if you like this type of videos and you don't want to miss out to another one. And if you have any questions on the laser technologies and the lasers that we talked about today, make sure to put a comment below the video. I'm already excited to read from you. And with that, as always, stay hydrated and see you in the next video. Bye bye.